Scientists have a way of looking at the world. I like to think of it as a way of knowing. And the way a scientist will proceed is to first observe nature and to look for patterns. And then, trying to understand that pattern, the scientist will develop an explanation of the process that produced that pattern. She will erect a hypothesis to explain the pattern that has been observed. Then the next step is to test the hypothesis. So either by an experiment or by simply gathering observational data, one tests the hypothesis. And then you can either reject the hypothesis or provisionally accept the hypothesis. And it's critical to understand here the way a scientist operates. A good scientist is never going to say, I proved that this pattern is caused by this process. What the scientist will say is, I failed to disprove that this process was the one that was operative. It seems like a trivial difference, proving versus failing to disprove. But a scientist is never going to assume that she or he has found the truth, that we test hypotheses, and if we're able to provide data that are supportive of the hypothesis, then we will provisionally accept it. But the next step would be to approach the hypothesis in a different way, to acquire different data, to try to knock that hypothesis down. So the process of scientific methodology is trying to disprove, not trying to prove. And if a particular hypothesis has been experimentally tested or observationally tested many times in many different ways, and every effort has failed to disprove it, then we may erect that hypothesis to the level of a theory. So in science, a theory is a set of hypotheses to explain the world that has withstood myriad efforts to disprove it. But even so, we would still not say that we have found the truth, that a theory is going to be a very compelling explanation, but we still leave the door open for possible disproof of that theory. One of the reasons that scientists try to disprove rather than trying to prove is to avoid something that's called confirmation bias. So confirmation bias happens when you have a great idea and you consciously or more likely subconsciously will allow yourself to emphasize observations that support your great idea and discount those that seem to be in opposition to it. And here's an example. One idea is that on moonlit nights that the incidence of violent crimes increases. So you can imagine the situation where we have an emergency room, and this emergency room has particularly high number of people coming in with gunshot wounds or knife wounds, and one of the workers in the emergency room says, "Wow, there are a lot of people that are coming in with wounds. The moon must be full." And someone else would say, "Yes, the moon was full. It was beautiful when I drove in tonight." And that supports this idea that violent crime is associated with moonlit nights. But let's imagine a different situation where a lot of people come in with gunshot wounds, and someone says again, "Oh, it must be the full moon." And someone else says, "Oh no, it was pitch dark when I drove in. The moon is new now. It's not a full moon at all." And then what people will do is to totally discount that. So they'll remember the fact that the moon was full when they had a whole lot of gunshot wounds and knife wounds, but the same incidence of those sorts of injuries with a new moon are going to be discounted entirely. It turns out that there is no effect of the moon on gunshot wounds and knifing. So this common knowledge that the moon is associated with crime does not hold up. but nevertheless it becomes confirmed in people's minds because they selectively remember data that support the idea and discount data that tend to negate it. Here's an example of the power of data and the power of anecdote. For years, people have been claiming that there is a relationship between childhood leukemia and proximity to high transmission power lines. And the idea here is that these electric fields are somehow causing children to develop leukemia, either because they were exposed as infants or because the mother was exposed while she was pregnant. And the National Cancer Institute conducted a 5-year study, spent over $5 million to examine this particular explanation. And what they did was to follow 638 kids that had leukemia and 620 that did not have leukemia. So they took tremendous amounts of information on proximity to high transmission power lines and to various other factors, diet and so forth. They also looked at where the mothers were when they were pregnant and were carrying these kids. And what they found was that there was absolutely no effect of transmission lines on childhood leukemia. So they said it was just simply time to stop wasting our resources on this question. Nevertheless, a few articulate parents can have a persuasive effect. So the general public will tend to be swayed more by an anecdote than by actual data. But someone who is statistically literate is going to abide by the National Cancer Institute study, where we're looking at a much broader scale. We're looking at over 1,200 kids. We get a much better picture of the problem, and a single anecdote, as statisticians say, does not make data. So the scientific method is an extraordinarily powerful way of looking at the world, and it essentially embodies the notion of skepticism. So we always want to be skeptical. We always want to take the show me attitude. We want to try to avoid confirmation bias. We always want to have the mindset that we're trying to disprove what our particular explanation is to explain a pattern in the natural world.